The one we're starting with is actually the same problem we did yesterday, but we're just going to go through the process of coming up with that function and then using the graph to maximize it. So we have this room, and we want to make an area like in the corner that's rectangular, and we'll call one of our dimensions x. Straight. And then we know that there's a total of 30 feet, and so if I use x feet for that wall, then there's going to be 30 minus x feet left over for the other wall. And then the big key, just like all other application problems we've done, the key to all of this is just getting the setup right. So we want to list all of our unknowns and assign anything we can to them so that we can go back and forth as we go through the different parts of the problem and we know what every single thing we find represents. So give me an unknown. What's one unknown in this problem?
X.
What does it represent?
I guess the amount of the dividers used on that side.
And we can look, if we look in part A, notice it says we want to express the area as a function of the length of the partition. And so when it says as a function of, that tells us what the input of our function is going to be. And so that can help us identify one of our unknowns. So the input of our function is going to be that length, and we're calling that x. What other unknowns do I have? The area, right? Because we are writing a function for area, which means that's going to be the output. So is my area. We'll call that A of x. What else? If my goal here is to write a function for the area, do I have everything I need listed there? Yes?
The width.
Yeah, we need the width as well, right? So width, and we said that was 30 minus x. And so now we've got all our unknowns. We've assigned either variables or expressions, and we know for the specific function that we're talking about which one is our input and which one's our output. All of those are important because when we have more than two unknowns, it can be hard to figure out what relationships we're using to find each thing. And so if we know what the input and output of our function is, then we're not going to try to plug something into one formula to get something else, right? We know exactly what we need to get everything that we're looking for. So we're going to start by writing a function. How do you find area?
Base times height.
So my length is x, and then my width is 30 minus x. And so simplifying that, I have a of x equals 30x minus x squared. And then we're given the graph of that function. So again, we just start out with labeling. When you get to part B of these multi-part questions, don't forget what you did in part A. You don't have to start all over again. You're using everything that you already did to do this second part. So the horizontal axis is always the input of your function, and the vertical axis is always the output of your function. So what should I label my horizontal axis? Mm-hmm. So these are my lengths. And what about my vertical axis? Mm-hmm. So I know for every point on that curve, the x-coordinate is the length, and the y-coordinate is the area corresponding to that length. So everybody see the local maximum? What does that tell me?
The dimensions that maximize.
Okay, so what do you mean by that?
So,
Well, like, go ahead.
The dimensions basically give you the most area for your problem. So like your x, where you plug, everyone has x in our equation, you plug in 15.
Mm-hmm. So what does dimensions mean?
Like your length times your width.
So the length and the width. So when we're asked to find dimensions, we're looking for length and width. And what does my maximum tell me? That ordered pair right there tells me what?
The area at the length of 15.
Okay, am I looking for area?
No,
So what part of that point do I need for what I'm looking for?
the 15.
Yeah, so this is my length, right? Because the x-coordinate represents length, is 15 feet. And then how do I find my width?
30 minus 15.
Right. You want to literally look for the word width. Like go up to your list and look for the word width. And it tells you exactly how to find your width, right? So 30 minus 15 equals 15 feet. When things go kind of awry on these problems, it's usually because people kind of get on autopilot and just start like plugging stuff in without really looking at what every formula gives them. So that's why we have that list there. And when you're looking for a width, you just go find the word width. If you're looking for area, go find the word area, and it tells you exactly how to find what you're looking for based on what you have. So the dimensions are 15 feet by 15 feet. And we don't need to say like the width is 15 feet and the length is 15 feet. We did that here so we could organize the pieces and make sure we got everything we needed. But in your sentence, like if we're talking about this piece of paper, like nobody's like, this piece of paper has a width of 8 inches and a length of 11.5 inches, right? Like nobody says that. Everybody just says it's an 8 by 11.5 inch piece of paper. So dimension, like the labels of length and width are completely arbitrary. We just kind of made them up so we could differentiate between the two dimensions. But once you're just saying the dimensions, it's just one number by another number. So you just list the two dimensions. And there's only two dimensions, guys. Like even if you have a full rectangle, you don't have to say what all 4 sides are because 2 of the sides are always the same, right? Both pairs. And so it's just length and width. So two-dimensional figures have exactly 2 dimensions. So let's use this same idea to help this farmer build a fence. So the farmer wants to put up a fence around a rectangular area that has 2 separate sections. So one of the other keys to these application problems, especially as they get longer and longer and more complex, is to like write things down as you go. Like don't try to read the whole problem and then do the whole problem. Once I read that I want a rectangular area that has 2 separate sections, I'm just going to pause and I'm going to make a rectangular area with 2 sections. Because then I don't ever have to read that sentence again. Because because I've recorded what it tells me. So then the longer side is up against a house, so we do not need fencing there. So we don't need fencing here, we'll say. And we have a total of 100 feet of fencing we can use. And part A says express the total area of the sections as a function of. So when I read the words as a function of, I think what I'm about to read is the input of my function. So as a function of, the length of the divider is going to be my input. So that's right here. So my input is the length of the divider which we're calling x. What is the output of my function going to be?
The total area.
Mm-hmm. So I'm expressing the area as a function, which means that my function gives me the area. So that's the output. Is total area. And we'll call that A of x. And then, James, do I have any other unknowns here? Have I listed everything I need to write that function?
I don't know.
Well, so what do you need in order to calculate area?
Length and width.
Have I listed both of those?
No.
So we still need
Width.
width. Good. And so we'll come back here and be like, okay, if the length of my divider is x, then this is going to be x, and this is going to be x. So making those three fences uses up 3x worth of fencing. And so I have 100 minus that left for the width of my, it is 100, right? Yes, 100 minus what I've already used left for the width of my field or whatever I'm building. So 100, which is what I started with, minus the 3x that I used to make those three lengths of fencing. So my width is 100 minus 3x. So if you list your input and output of your function and you're not sure if you have other things to worry about as far as other unknowns or things you need to assign a variable to or an expression to, ask yourself, just like we did there, like, have I listed everything that I need to calculate the output? So in this case, the area. We think I need a length and a width, and I've only listed the length, and so we need to write something about the width. And that can help you figure out if you have everything you need in your list. So now we can write a function. Grace, how do I find the area of a rectangle?
Is it just length times width?
Uh-huh. So I look for length, it's x. And I look for width, it is 100 minus x. Or sorry, 100 minus 3x. So notice I'm using what I already did. What makes these even harder than they have to be is if you try to start from scratch every time you do a step. So the reason we have this whole setup is to make the rest of the problem fairly simple, because once we've written that list, if I say area is length times width, I look for the word length and it tells me exactly what to write for length, and I look for the word width and it tells me exactly what to write for width. So now we can simplify this guy. I have a of x equals 100x minus 3x squared. So now I have a function for my total area, and we're ready to maximize it. So let's see. Anna, what should I label my horizontal axis?
Length.
Length, very good, because that's my x value, that's my input. And again, all I'm doing is looking at my list where I wrote input and output to figure out what my horizontal and vertical axes are. So Holly, what should I label my vertical axis?
Y-axis or Y length? Your vertical?
So x represents the length. It might help if you weren't on your phone. Because I just told you guys how to find it. Somebody else help me out. Yeah, it's the area because I'm just looking at that list and identifying my input and my output. So my input was length and my output is area. What am I looking for here, Dan? What's my final goal?
What you can plug in, pretty much. No?
What do you mean?
You should go A of x, 100, x, and bx squared. Just basically looking at your thing there, what you can plug in.
Okay. What's the question asked me for?
Determine the dimensions that maximize the area.
Right, so I want my dimensions, right? And again, dimensions just means length and width. So I want a length and a width. Reeve, do I know either of those from my graph?
The length is 16.7.
Very good, because that's my x-coordinate. We know my x-coordinate represents length. So 16.7, I think we're in feet here. And Nina, what about my width? What should I do to get that?
10 minus 3 times 16.7.
Good, yep, we just look at our list.
Sorry.
Oh, no, you're fine. We just look at our list and we find the word width and say, okay, this tells me to do 100 minus 3 times 16.7. And I think that's 49.9, but you might want to double check that I did that right. And so now I can write a sentence. The dimensions are 16.7 feet by 49.9 feet. So this is kind of the general process for all of these problems, these maximization problems, is just making this list, writing a function, and then listing out what it is you're trying to find, and then going back to all the information that you set up for yourself and finding it. Again, the setup is worth the time because it saves you a ton of time later because you don't have to spend a bunch of time trying to find everything and figure out what's what. So let's talk revenue. So we've seen problems like this before, but we've just done like the first half. So we'll do the same thing we did before. We're going to start with, and some of these problems you kind of have to read through the whole thing to figure out like what your function is. Like the goal of this entire thing, all the parts of it, is to maximize something. And so if we look at our graph, the goal is going to be to maximize revenue. So the thing that you're trying to maximize in the long run is what you want your output to be, what you want your function to represent. Because if we wrote like two separate functions for like parts B and C, then we can't use them together to get what we're trying to find. We have to like reinvent the wheel. So you want to, from the very beginning, just like we did in the last problem, be like, okay, I'm going to have one function, and what's the output of my function going to be?
Price of tickets.
So, yeah, it's the revenue because that's what I'm trying to maximize. So your function will always be whatever it is you want to maximize and or minimize. So revenue, which we'll call R of X. And then what's the input of that function going to be? What variable is the input? It's X. Yeah, good. So we see here that our input is X, and then right here it tells me that that's quantity. It also tells it to me here. So there's a couple places you can find that, but whatever's inside the parentheses right here is the variable, and then you just look to see if they told you what that variable represents. So my input is going to be quantity, and we're calling that X. Do I have any other unknowns? What?
Price per ticket.
Yeah, price per ticket is my other unknown. And I don't have a super obvious way to find that if I know X, right? There's not like some sentence in the problem that says it's 3 more than 2 times the quantity or anything like that. So because there's nothing that immediately comes to mind, I'm just going to call that P. I recommend that you do not use the variable Y in these problems, only because when we get to the graph, your Y coordinate might not be what you called Y, and that can be really confusing to have one thing be Y but not have it be the actual Y coordinate. So that's why I use P there, just so I don't confuse myself. So let's make this table here. So if the quantity is 31, what's my price going to be?
975.
Mm-hmm. And if my quantity is 32?
950.
Mm-hmm. Does anybody know what it is if my quantity is 40? 750. And then what's my revenue at a quantity of 31?
302.45.
Good. And we got that just by multiplying price times quantity. Did you say 75 cents?
45.
Okay, thanks. And for 32?
304.
And 40. So the table's kind of nice just because it gives me a little bit of a framework. If I'm maximizing revenue, one thing I notice is that from 31 to 40, my revenue goes up and then it goes back down, which means that whatever quantity maximizes revenue, it's got to be between 31 and 40, right? Because between those two inputs, my revenue increases and then changes to decreasing. And so if I solve this problem and I get like a quantity of 6, then that's a red flag that I probably did something wrong and I should go check all my answers. So now let's look at B. I want to write a linear equation that models the price if X people are on the tour. So I'm looking for a relationship between quantity and price. If the equation models the price, that tells me that the price is like my Y value. So I'm going to write ordered pairs that are quantity, price. And I know that I can use points to find a slope and write an equation because I was told that it's a linear relationship. I couldn't go down to part C and be like, okay, I'm going to write 2 points, find the slope, and write a linear equation, because I don't know that revenue is a linear function. It doesn't say anything about that. But here, since I'm told in part B that there's a linear model, then I know that I can find the slope and then write in slope-intercept form. So we need 2 points. we'll use 3010 and 31,975. So I want to start by finding my slope. So 975 minus 10 over 31 minus 30, which is going to be negative 0.25. And you might notice that that number is like in our sentence too. It turns out, remember, the definition of slope is the change in the y value when the x value increases by 1. Well, up here we're saying that we're increasing the quantity by 1, and the result is a decrease in the price by 25 cents. If you see that and you can interpret that as the slope is negative 0.25, then by all means you don't have to do the slope formula. So it's given to us in two different ways. If all else fails, grab 2 points and calculate the slope. But if you can get it from that sentence, then you're more than welcome to use that. You get the same thing either way. So now what are we going to do with the slope to write an equation? So we're going to start with our slope. And we're going to set it equal to our slope formula, replacing one of our points just with the ordered pair QP. Right? We're writing the formula for the slope through the point XP and 3010. Because that has to be equal to our slope. So we have P minus 10 over X minus 30. So we'll clear fractions. Distribute. And then we want to solve for P because we want our equation to give us the price. So we want P to be alone. So we have negative 0.25x plus 17.5 equals P. So if I look back at my list, when you make this list, you want everything to be in terms of your input, so in terms of x. What we have right now is this P at the bottom, which is not in terms of x, right? It has a different variable there. And so the reason that we did this process in part B was so that we can replace that P with something in terms of x. So just like we had here, right, that last unknown, we had an expression that contained only x. And so that's our goal here. It wasn't quite as easy to get to as on the last one. We had to do a little bit more work, but now we can replace P with negative 0.25x plus 17.5. And we have to do that before we can write our revenue function. We have to get all our unknowns in terms of our input, in terms of x, because I'm not allowed to have more than one variable in my function. So now, how do you find revenue?
Quantity times price.
Yep, revenue is quantity times price. And that formula will be on the test. So we have R of x equals We look for the word quantity, it's X. We look for the word price, negative 0.25x plus 17.5. And then we'll distribute. Plus 17.5x. And that's our revenue function. So if we do all our setup at the beginning, then that last step to write the function isn't too bad, right? We're just pulling from our list of unknowns. Now we are going to use our graph to maximize revenue. So this graph is a discrete graph instead of a continuous graph, meaning that it's individual points rather than a curve. And that's just because you can't have like part of a person on the cruise or tour, right? So it wouldn't make sense for our graph to go through a y value of like 12.5, right? So that's the only reason. It behaves the same as far as what we're doing as the one that was just a solid curve. So what is it that I am looking for, Kenny?
The dimension, the price and number of people.
Good. So I want a price, and I want the number of people, which is just another way of saying quantity. Let's label our graph. Jess, what should I label my horizontal axis?
That's gonna be the number of people.
Good. So that's my x value, my input. And because you never know like what variables might be floating around your problem, always when you look for what to label your axes, look for where you said input and output, not necessarily like x and y, right? They could have said that quantity was represented by q, and then that's the variable we would have used, but we would still label our x-axis quantity. So you want to think of your horizontal as your input and your vertical as your output, and rely on that more than like x and y per se. So what should I label my vertical axis, Anna?
Price?
So what's my output?
Revenue.
Revenue, good. It can be tempting to label it based on what we want, and you want to just remember to label based on what you have, so the list that you made. And the more information you have in your list, the easier it's going to be to get those pieces. So what do I know, Trey, from this graph?
We know that the quantity's gonna be 36,
Very good. So my x-coordinate is 36.
and your y's gonna be 306, or your r of x, I guess, is gonna be 306.
Yeah, r of x is going to be 306. Good. So quantity is 36. What about my price? Is that 306? No, that's my revenue, right? How do I find my price? Caitlin.
The negative 0.25 times 36 and then add 17.5.
Very good. We just go back to our list, we find the word price, and it tells us exactly how to get it, right? So negative 0.25 times my x value plus 17.5, and that is 850. So revenue will be maximized at a price of $8.50 per person for a group of 36 people. And we're done. So tonight you have just a worksheet. You don't have any of my math lab. So I'm going to hand that out now. And in the 10 minutes we have left, I want you to try to do one problem on your worksheet before you go. Just so you get a little bit of practice on your own before you walk out the door. So